we did two things when we looked at production, or two things that you should take key learning outcomes from last week. The first was that relationship between inputs and outputs. If a firm uses a certain amount of factor inputs, and the example we used were labour and capital. Two examples of factors of production. The firm combines them. How much output can it produce? That relationship between the two was defined by the production function. Now, we looked at the production function when we brought it right to the end of last week's lecture. We actually looked at the production function in two ways. We looked at it in the short run and in the long run. We defined that period of time, the long run, as that period over which a firm is able to freely substitute all of its factor inputs, that nothing is fixed. It can increase its labour or decrease its labour. It can increase its capital or decrease its capital. In the long run, everything is variable. Now, in the short run, though, that alternative time period, only one factor input is variable. So given the way that we set it up, we said that labour is the variable factor and capital was fixed. So in the short run, a firm would operate with a fixed capital stock and could only increase or decrease its output by adjusting the amount of labour it used. So those were the two time periods, the short run and the long run. And that encapsulates what we did in last week's lecture. Now, what I'm going to get you to do today, what you're going to learn from today, is we've said how a firm combines inputs to produce output in the short run and the long run. What we're going to look at for today's lecture is how does a firm choose the optimal mix of inputs to produce its output in both the short run and the long run. So we know how inputs translate to outputs. What we're now going to do is what is the optimal mix of inputs, the optimal combination of labour and capital to use in both the short run and the long run. Now, to avoid, and this makes it a little bit easier for you as well, to avoid problems associated with market power, and indeed market power is going to be our next topic, when we look at this question of what are the optimal inputs to use, we're only going to look at the scenario, only look at the case of a price-taking firm. That is a firm without any market power. And we're going to abstract from this idea of market power in both the factor input and output markets. Now, what does that mean? A firm who's a price taker in the factor input market means that they can employ as much labour and capital as they like. Their actions don't affect the price they would pay for labour and capital. They're a price taker. Now, in the product market, what do we mean by a price taker? We mean a firm can produce as much output as it wants, and this does not affect the market price. So its actions don't affect the market price for the output market. They don't affect the input price in the factor input market. So we're looking always at the case of price-taking behaviour. So, with that in mind then, we're going to look at this sequentially. First of all, we're going to look at a firm, a price-taking firm, in the short run, and how a firm decides upon the optimal mix of factor inputs. Then when we've done it for the short run, then we'll look in the long run, that time period where everything is variable. So, that's the scene set. So, firstly, how does a firm choose what factor inputs to use to produce its output in the short run? That time period over which only one of its factor inputs is variable. Well, I'm going to tell you something now, and right at the end of this first part of the lecture, I'm going to return exactly to this phrase here. How does a firm choose the optimal mix of inputs to produce its output in the short run? Well, the very, very simple idea is a firm will wish to continue to use factor inputs as long as it is profitable to do so. And I guess there's absolutely no contention about that. It's fairly obvious. A firm, if we're talking about the short run, and we'll say that labour is our variable factor, a firm will continue to employ labour as long as it's profitable to do so. Sounds fairly obvious. Okay? And we'll return to that exact phrase right at the end. So, I've said first of all, as long as it's profitable to do so. Well, for a firm, what are profits? Profits are merely the difference between revenue and costs. So even though some of this lecture, it might look as if there's a lot of algebra in it, it all boils down to very, very simple concepts. And this is our starting point. That's all you need to remember in what follows. That profits is the difference between revenue and costs. How much do I get for selling this output? How much does it cost me to produce this output? Difference between the two is profits. So now, I'm just going to throw a tiny, tiny bit of algebraic notation at you. And that's all it is, just a bit of notation. So we will denote profits by pi. Well, what is revenue? Well, revenue is just price times quantity. P, we'll say, is the market price for the output that the firm produces. And X is the level of output the firm produces. So P times X, price times quantity, is revenue. That is revenue. Minus costs. Well, where do costs arise for this firm? Well, costs arise from the cost of employing the variable factor production plus the cost of employing the fixed factor of production. So, labour is the variable cost of production. Capital is the fixed factor of production. So, the variable cost is the cost of employing labour. That's the wage rate, which is the unit cost of labour, times L, the number of units of labour employed. So W times L is the total wage bill. R is the unit cost of capital, and K is capital. So the unit cost of capital times the capital stock, which we said was fixed at K, when in the short run, capital is fixed. So R times K is the cost of employing the fixed factor of production. So there you go. That's all that profits are equal to. Revenue minus the variable cost of production minus the fixed cost of production. And it's as simple as that. Now all we're going to do next is take that expression there and just rearrange it in terms of X, in terms of output. Now I won't put any intermediate steps there. It's just simple bit of algebra. You can work it through for yourself. But if you take that, rearrange it in terms of X, that's what you get. Pi divided by P plus W over L divided by P plus RK divided by P. Simplify a little bit more, then you get that expression there. And what that is telling us is that there is a relationship between output and labour. X is the output, L are the number of units of labour employed. And that is the relationship we want to find. Because that there is a very, very specific form that's useful for us. That equation, as I've described it there, that equation between output and labour describes what is known as the firm's ISO profit line. So when we looked at last week, we had an isoquant, a curve that showed equal quantities. That term in the front, iso, meaning equal. What we've got here is an iso-profit line. So it's equal profit, a constant level of profit. And so this expression here that shows the relationship between output, X, and the number of units of labour used, that is an iso-profit line. It shows output levels that yield a constant level of profits. So equal profits. So all of those output levels a firm can produce that give it exactly the same level of profits. That is an iso-profit line. And that equation there perfectly describes it. Now if I were to ask you to look at that expression there, what should jump out at you? If you all go back to your Maths 101, very, very first thing you would have learnt about algebra. That is the equation of, anyone want to shout it out? Anyone not want to shout it out? That is the equation of a straight line, where it has, it's a relationship between x and L, but it's a linear relationship, where that first term represents the vertical intercept, and that term in front of the L represents the slope of the line. So were we to graph that iso-profit line, what we'd end up is something like the following. Now whenever you draw these diagrams, the first thing you need to remember is what is on the axis. So for example, when we looked at isoquants last week, what was on the axis? That was our factor inputs, labour and capital. We don't have labour and capital on these axes. What we're showing is a relationship between output, X, and labour, L. So that is what's on the axis, output and labour. And that solid line in the middle represents an iso-profit line. It shows us output levels that yield a constant level of profits. So along this particular along that particular iso-profit curve, the level of profits is fixed. Output is increasing. We produce various levels of output, but each and every level of output gives exactly the same level of profits to the firm, pi. Specifically though, what about that term there? And what about the slope? Well, we said that iso-profit line, the equation gave us the vertical intercept and it gave us the slope. So the vertical intercept is that first term there. Pi plus r times k, which is our fixed cost, divided by p. So pi plus rk divided by p. That is the vertical intercept. And the slope of the iso-profit line is plus, so it slopes upwards. It's got a positive gradient, w over p. So the slope of that line is w over p. And as I said, the level of profits along that particular iso-profit line is fixed. It's constant. What then about these other lines in the diagram? Well, again, I want you to go back and think about the intercept here. The intercept is profits plus fixed costs divided by P, the unit price of output. Well, we're talking about the price-taking firm. There's nothing that the firm does that affects fixed costs, nor the output price. So we can take those as given. So if that's the case, if fixed cost is fixed, if the market price of output is fixed, what's the only other way in which that vertical intercept could move? It would be if profits changed. And so if profits increased, that vertical intercept would increase. So, for example, if profits went up from pi to pi 1, increased, that vertical intercept would also increase. And hence, this higher ISO profit line here is associated with a higher level of profits. And indeed, anywhere along this ISO profit line, profits are fixed or constant at pi 1. And in exactly the same way, what about lower ISO profit lines? Well, again, along any given ISO profit line that's lower, profits are fixed. But the fixed level of profits on these lower ISO profit lines are also lower. So in the diagram here, we've got a certain level of profits, pi 0, which is less than that level of profits pi, which again are both less than that level of profits pi 1. So even though we started off with one ISO profit line, there are a whole family of these ISO profit lines that will have, each of them will have a slope of W over P, the wage rate divided by the price of output, and higher ISO profit lines are associated with a higher level of profits. So, were I to ask you the question, what does the firm want to do? Of all those ISO profit lines there, which one would the firm rather be on? They have the choice of being on that one there and enjoying a level of profits pi 1, or have the choice of being on that lower one there and enjoying a profits of pi 0. So if I asked you that question, the answer would be fairly obvious. The firm wants to make as much profit as possible. Therefore, it wants to be on its highest possible ISO profit curve. But there's a problem, or there's a constraint that the firm faces. Of course, it wants to be on a high ISO profit line as possible. But the constraint is, what can it produce? It's subject to this constraint that it can combine labour to produce a certain amount of output. And what is that constraint determined by? That constraint is determined by the firm's production technology, or its short-run production function. And that's the other part that we need to bring into it. We've got these ISO profit lines, and a firm that wants to maximise profits will wish to be on the highest possible ISO profit line. But its ability to reach any ISO profit line is subject to its production constraint, subject to the constraint of its production function. And so, that's what we need to do, to find out of all these ISO profit lines that a firm faces, which is the highest one it can reach. Well, it's that one which is also along its production function. So, what we've got here is the same sort of diagram as before, where these straight lines are just pi 2, pi 1, pi 0. Those straight lines are just the ISO profit lines as before. All I've now done, though, is put that S-shaped curve on there. That, if you can remember from last week's lecture, if you can't, doesn't really matter. But what that curved line is the firm's short-run production function. That showed us the relationship between inputs and outputs with a fixed capital stock. And if you can remember, if not, I'll remind you, the reason we drew it in that particular shape is initially there's a period of increasing marginal returns to labour, so that production function gets steeper. Then we have a period of constant marginal returns, where our short-run production function is a straight line, before eventually diminishing marginal returns set in. That is, successive units of labour add less to output than preceding units of labour. And so in general, I said, it doesn't matter what our factor inputs are, it doesn't matter what production technology we're employing, typically a short-run production function will exhibit that shape. The law of diminishing marginal return says at some point eventually diminishing marginal returns will set in. So that is our typical short-run production function. So the question is, of all the points along that production function, which one does the firm produce? Well, we said the firm wants to maximise profits. It wants to be on the highest possible ISO profit line. So, for example, if you gave the firm the option of that ISO profit line there, enjoying a high level of profits by 2, would it like it? Simple answer is yes. But the problem is that particular ISO profit line is not attainable. Given the technology that the firm employs, it can't use labour to produce output that allows it to attain that particular ISO profit line yet. It's just unattainable. So, what then about point A? Is that an obtainable point? Well, it's on the production function, so if the firm wanted to combine that amount of labour to produce that amount of output, it could do so. Its production technology would allow that. That's totally feasible. And what does it mean about the profits at point A? Well, if we drew the ISO profit line that passed through point A, it would be that ISO profit line there, pi 0. So it's obtainable, and it yields a certain level of profits. But is that the best that the firm can do? Simple answer is no. Because the firm could reorganise its production, it could use even more labour, expand its workforce, and produce more output, and move from point A towards point B. And as it's moving along its production function towards point B, what do you notice about the ISO profit lines? That they're getting higher and higher and higher. Therefore, the firm's profits must be increasing. And this process will continue until the firm has moved from point A to point B. Where point B, it's on the production function, so it's feasible. But at point B, the production function, the short-run production function, and the ISO profit line pi 1 just touch one another. They're tangential. That means there isn't a higher ISO profit line that exists that still touches the production function. And so, that denotes pi 1, this level of profit here, denotes the highest level of profits the firm can make given its production function. And that is the profit maximising point, where this firm would optimally choose to employ L star units of labour to produce X star units of output and enjoy a level of profits pi 1. It could not reorganise its production such that it made a higher level of profits. And that is the optimal amount of labour, and therefore by extension output, the firm should employ. But what I want you to do, just before we go on, is just look at that part of the production function, where point B is tangential. Now, our ISO profit line is a straight line. Could you draw a straight line that was tangential to the production function anywhere indicated on the diagram, where that curve is getting steeper? Think about it, you couldn't. A straight line would always intersect anywhere here, where that production function is getting steeper. The only place where we could possibly get a tangency is where this production function, the slope, is beginning to get shallow, where the curve is then going down. That's the only way. If you look at the diagram, that could possibly happen. But what does it mean though? And we'll pick up on this a little bit later. This means point B must be somewhere where there are diminishing marginal returns to labour. That is, the marginal physical product of labour must be declining. That's what it means on that part there, where the slope is shallow enough. There's no way you could draw the straight line that was tangent on anywhere, for example, at point A, or down here where we have increasing marginal returns. Isoprofit line would cut the production function. If it does that, it isn't profit maximising. So, for the moment, we'll return to that in a short while, but for the moment, what does point B suggest then? We've got a tangency between isoprofit line and the short run production function. At the beginning of this lecture, I said that the slope of the isoprofit line was W over P. That was the wage over the price of output. That was what the slope of the isoprofit line is. We've also said previously that the slope of the short run production function equals the marginal physical product of labour. The marginal physical product of labour, just to remind you, shows how much extra output an additional worker adds. So if you apply one extra worker, how much more output does he or she produce? That extra output is the marginal physical product of labour. And the slope of the short run production function, as we saw last week, is equal to the marginal physical product of labour. So that is what we identified at point B. And that will always be the case. That is our profit maximising condition. I just want to rearrange it ever so slightly though. I want you to multiply both sides by P. So that gives us W equals P times the marginal physical product of labour. And if you take the marginal physical product of labour and multiply it by price, you get the marginal revenue product of labour. Now, by its very title, the marginal physical product of labour looks at physical units. If you employ one extra worker, how many physical units of output does that worker produce? How many additional units does he add to total output? That's the marginal physical product of labour. Marginal revenue product of labour is not interested in physical units, but it's interested in price. All of these extra units, all of these extra units that worker produces, how much can they be sold for? What value can the firm sell them for? That is the marginal revenue product of labour. So it's equal to physical product, marginal physical product, times price. So if you think, what have we found here? We've said that a profit maximising firm, if labour is its variable input, will maximise profits when wage is equal to the marginal revenue product of labour. That's all that we've got here. And that's uncontentious. And this goes back to what I said right at the beginning of the lecture. A firm will continue to employ labour so long as it's profitable to do so. If it's not profitable, you don't employ the labour. If it is profitable, you do employ it. That is all that expression there is telling us. And if you don't believe me, I'll show you in the following diagram. So, what we have here is labour on the horizontal axis and wages, the price that we pay for labour. And what I'm going to show you here is the firm's short-run labour demand schedule, or its short-run factor demand schedule. Like most demand curves, virtually all demand curves, it will be downward sloping. That is the firm's short-run labour demand schedule. Why, though, does it look like that? Well, think about what we found. We said that to maximise profits, a firm should equate wages with the marginal revenue product of labour? Well, let's take a step back. Forget that that is the short-run demand for labour schedule. That schedule, as slopes downwards, is also the marginal revenue product of labour. It's equal to price times the marginal physical product of labour. Yep, that's marginal revenue product. Marginal physical product times price. Now, why have I drawn it as downward sloping? Am I assuming something here? Or maybe I'm relying upon something that I asked you to know 10 minutes ago. When we looked at point B, what did we say? Point B, that profit maximising point, must lie on that sort of section of the production function. That point where we have diminishing marginal returns. That is, the marginal physical product of labour will slope downwards. So profit maximisation can never be where we have increasing marginal returns. I mean, if you wanted to, you could think through it logically. Won't even go through that. Maybe you can tease that out in seminars. But from this diagram, the only part of the schedule where we're going to get profit maximisation is we have diminishing marginal returns. The marginal physical product of labour schedule slopes downwards. So there you go. The only relevant portion of marginal physical product is where it slopes downwards. So if you take marginal physical product, which slopes downwards, multiply it by a constant price, that schedule is still going to slope downwards. And that is the marginal revenue product of labour schedule. So, what will a firm do? Maximise profits by equating wage with the marginal revenue product of labour. Well, we're talking about a price-taking firm. I said a firm has no ability to influence the wage rate. If it employs one worker, if it employs 1,001 workers, makes no difference. It still pays each and every worker exactly the same. Its actions do not influence the wage rate. That's what we mean by price-taking behaviour. So it will pay its workers a constant wage rate. It doesn't matter how many of them it employs. So, given that constant wage rate, how many workers would the firm wish to employ? It would adopt that profit maximising rule of equating wage with the marginal revenue product of labour, which in the diagram occurs there. So optimally, the firm will wish to employ L star units of labour. But if the firm were forced to if the firm were forced to pay a higher wage rate, so the wage was up there, how many units of labour would it employ? Well, it would then reduce the amount it employs. If it could pay a lower wage rate, it would increase the amount that it employs. And all of these levels that it chooses to employ would trace out this marginal revenue product of labour schedule, which is why that marginal revenue product of labour schedule is also the short-run factor demand schedule. Now what I want to do is bring this all the way round to that very, very first thing I said. And I want you to think about that diagram. I want you to think about that diagram intuitively. We said a firm will continue to employ labour as long as it's profitable to do so. As long as it's profitable. What does that mean? It means what it costs to employ the labour is less than the value of output. If it costs you £10 to hire one extra worker, but that worker can produce output that is worth £20, would you take that worker on? Yes, because it's profitable to do so. If you had to pay a worker £10, but that worker could only produce output which is worth £7, is that profitable? No, it costs you more to employ them than the value of output. And that is exactly what we've got in this diagram. Anywhere to the left of L star, the wage rate, that is what it costs to employ a worker, is less than the marginal revenue product, the value of output that worker can produce. So anywhere below L star, the cost of employing a worker is less than the value of output. Therefore, it's profitable to employ these workers. And that is exactly what the firm will do. That takes us all the way up into L star, and anywhere to the right of L star, the cost of employing an extra worker is still the fixed wage rate. But what output, what value of output do these workers produce? That's given by the marginal revenue product, which is less. So for these workers, beyond L star, the value of output they produce is less than the cost of employing them. And hence, it isn't profitable to employ these workers. And so the firm doesn't bother. It will only employ workers up until that point of L star, where the wage is equated with the marginal revenue product of labour. So that then is the short one. Before I give you your break, I want to briefly give you an introduction to the long run, and now that will then set the scene for what we're going to do in the second lecture. Now, the long run is more complicated by the very nature of the fact that a firm can freely substitute one variable factor for another variable factor. So we can't just repeat what we've done in the short run. So what we're going to do is look at exactly the same idea. What optimal mix of inputs does a firm use to produce its output such that it maximises profits? Well, what we're going to do is split this into two separate conditions. We'll look at each of these separately. So the first thing is, for any given level of output, what way should a firm combine its factor inputs such that it produces that output for the least cost combination? I.e., what's the cheapest way of combining labour and capital to produce a given level of output? So that's the first step. Find the minimum cost, the least cost combination way of producing any given level of output. And then, once we've identified all of these least cost combination ways of combining factor inputs, we then want to identify the most profitable level of output. So first of all, the first part, cost minimisation. What way does a firm combine labour and capital in the long run to produce output for the least cost? What's the cheapest way of producing any given level of output? Well, in the same way as we saw with the ISO profit line, we start off with a very, very simple idea. This time, we start off with what are production costs? And give a little bit of algebraic representation that follows, but the starting point. What, for a firm, is the cost of production? Well, the cost of production is merely the cost of hiring all units of labour, plus the cost of hiring all units of capital. So, that's what it is. Using notation that we've seen before, we'll say that costs are C. That's our total production costs. Well, W times L. W, as we saw in the previous lecture, is the unit cost of labour, times L, the number of units of labour employed. So W times L is our cost of hiring labour. R times K, where R is the unit cost of capital, times K the number of units of capital employed. That's our total cost of hiring capital. So that is our total production costs. Notice though, in comparison to what we saw previously, I've now dropped the bar on that K. We put the bar on the K previously to denote the fact in the short run the capital stock was fixed. The firm could increase, it couldn't decrease the amount of capital it employed. Now, what about the long run? That time period over which all factor inputs are variable. And so, I've dropped that bar over the K. Now, all I want to do, in a similar way as we saw previously with the ISO profit line, is just take that expression there and just rearrange it. This time, I want to rearrange that in terms of K. And that's what I do. K equals something related to L. So there's a relationship between capital and labour. And that is what we've described here. It's a simple little bit of algebra. I'll let you put in the steps in between those for yourself. But that relationship between K and L, that expression that I've derived there, just from that very simple idea here, is an ISO cost line. So we've seen ISO quants. 30 minutes ago, we saw ISO profit. Now what we've got is an ISO cost line. And an ISO cost line is equal cost. More specifically, it's a combination of our factor inputs. It's our combinations of labour and capital that cost the firm the same amount to employ. That is an ISO cost line. And if we look at that ISO cost line that we derived here, what else do we notice about it? Well, again, if you think about what happened with the ISO profit line, that was the equation of a straight line. That ISO cost line is also the equation of a straight line, where that first term is the vertical intercept. That second term in front of the L is the slope of that line. So starting from that very, very explanatory starting point, production costs, cost of hiring labour, plus the costs of hiring capital, can easily derive that expression there, which is the firm's ISO cost line. Combinations of factor inputs that cost the firm the same amount. So that's the ISO cost line. What would it look like if we graphed it? Well, remember what's on the axis. It's a relationship between K and L. So that's what you should have on your axis. So, K, capital, labour, L. That's what's on our axis. And I said the ISO cost line, I'll draw it there again for you, was a straight line, was the equation of a straight line. So there you go. That downward sloping line is the ISO cost line. Combinations of capital and labour that cost the firm exactly the same amount to employ. So they're different combinations of these factor inputs, but what does it cost the firm to employ these various combinations? Exactly the same. That is the firm's ISO cost line. So, I said that was the equation of a straight line. That's the way that I've drawn it. So, that equation of a straight line gives us two key bits of information. The first is the vertical intercept. So that vertical intercept here is C over R. That's total cost divided by R, the unit price of capital. If we wanted to find that intercept here on the horizontal axis, how might we find that? Well, this is just capital equals 0. So when the firm employs 0 units of capital, and it only employs labour, we're at that point there. So if I set K equal to 0 in that expression, and worked out what L would be, again I'll leave this to do it for yourself, but jump in straight to the answer. that point there, the horizontal intercept would be C over W. Total cost divided by the unit price of labour. So there, we've got cost divided by the price of capital. We've got cost divided by the price of labour. And what's the slope of that isocost line? It's minus, so it slopes downwards from left to right, W over R. That is the ratio of the cost, the price of labour, to the price of capital. Now, I've emphasised all the way along price. Now, why have I done that? Hopefully, what it will do, it will resonate with you, the similarities between that curve that we've got there, that ISO cost curve, and a budget constraint. Now, when we look at a budget constraint, what key information do we have? We have the vertical and horizontal intercept, and we have the slope. So a budget constraint, what would the vertical intercept be? It'd be income divided by the price of the good on the vertical axis. The horizontal intercept would be income divided by the price of the good on the horizontal axis. And the slope of a budget constraint measures the relative prices of the two goods. The ratio of the price of the good on the horizontal axis to the price of the good on the vertical axis. So in that regard, there are distinct similarities between a budget constraint that you've seen previously and that ISO cost curve that we've got here. The only difference is that an ISO cost curve is drawn for a fixed level of cost. A budget constraint is drawn for a fixed level of income. And that's it. Apart from that, if everything I've said, you substitute cost for income, or income for costs, that would behave in exactly the same way as a budget constraint. So, for example, with a budget constraint, if the price of the good on the horizontal axis increased, what would happen to the budget constraint? It would pivot inwards. And that's exactly what would happen with the ISO cost curve. If the price of labour increased, our ISO cost line would pivot inwards. Or, if the price of the good on the horizontal axis decreases, our line would pivot outwards. And as we move to higher budget constraint, it reflects higher income. As we move to a lower budget constraint, it reflects lower income. Or just substitute cost. As we move to a higher line drawn outwards, a higher ISO cost curve, that represents a higher level of cost. As we move inwards towards the origin, that represents a lower level of costs. So in those regards, the way that we draw and manipulate a budget constraint and ISO cost curve are exactly the same. However, whilst I've drawn these analogies with the theory of consumer choice, remember what we're trying to do. We're trying to find the minimum cost combination of producing any level of output. And at this juncture, these similarities with the theory of consumer choice stop. So whilst this diagram here might look very, very familiar to you, its interpretation is somewhat different. So, what are we trying to do? We're trying to find the minimum cost way of producing any given level of output. So what I've done, I've taken an arbitrary level of output. A level of output of 10,000 units. And that line here is that curved line is our ISO quant. That curve that we've seen previously, combinations of factor inputs that yield a constant level of output. So the question we want to ask ourselves, of all the ways that we could produce 10,000 units of output, which combination of labour and capital minimises the cost of doing that. So, let's say that we're at point A. Point A is a combination of labour and capital that lies upon our isoquant for 10,000 units. So we could combine labour and capital together to produce 10,000 units of output. What does that imply for costs? Well, to find the costs associated with that input combination at point A, we would draw the ISO cost line that passes through point A. So with a given price of labour and a given price of capital, our ISO cost line will have a certain slope. And that will define ISO cost line I2. The question I want to ask you, and hopefully you'll all see what the answer is, or you'll know what the answer is point A the cheapest way, the least cost way of producing 10,000 units of output? Hopefully you can all see the answer is no, because the firm could combine a different combination of labour and capital that allowed it to reach a lower ISO cost line. And if it reaches a lower ISO cost line, it incurs less costs. And that's what we're trying to find, the cheapest way of producing this given level of output. So, as we move along the isoquant from point A towards point B, you can see that the ISO cost lines that would be on would be closer to the origin. They're cheaper ways of producing the output. And this will continue until we arrive at point B. We're at point B, the ISO cost line, I1, just touches the ISO quant associated with our 10,000 units of output. And it just touches at point B, and that suggests an output combination, input combination I should say, of K star units of capital and L star units of labour. It wouldn't be possible for the firm to still produce 10,000 units of output and combine labour and capital in a way that's any cheaper. And so, point B reflects the least cost combination way of producing our given level of output. However, what I do want you to note though is the difference in this analogy between isoquants and isocosts that we've got here with that story of the theory of consumer choice. In the theory of consumer choice, you have a fixed budget constraint and you look to identify the highest possible indifference curve. Here though, even though the diagram looks remarkably similar, what's fixed is the isoquant. Isoquant associated with our level of output is fixed. And given this fixed isoquant, what we then look to do is identify the lowest possible ISO cost curve. Once we do that, that's the least cost combination way of producing any given level of output. So, that's the first part. We can take any level of output, and the least cost combination way of producing that is by finding the lowest possible ISO cost given the isoquant. Do it for every single level of output we're concerned with. This is probably the trickier part now to get your minds around. It's that second part. And this is choosing the most profitable level of output. The diagram that I'll show you at the end is really, really simple. It's a diagram that you all know. It's the long run average cost curve. And the outcome is obvious. But it's how we get there can be a little bit trickier. So, I'll take it as slowly as I can. So, of all of these output levels, a firm could produce in a least cost combination way, which one is the most profitable? Well, the answer to that question is that it all depends upon returns to scale. Now in seminars this week, in seminars last week, you were going through discussion sheets, lots and lots of questions on there on returns to scale. giving you production functions, and you need to identify, is it increasing, decreasing, or constant returns to scale? So, I won't use Kahoot, but I'll throw a question out for you in a moment. So, this again is our standard diagram, ISO quants and ISO cost curves. So we've got our factor inputs, capital and labour on the axis. Let's say that we've got our initial ISO quant for 10,000 units of output. The least cost combination way of producing 10,000 units of output is when the firm is on its lowest possible ISO cost line. That is that ISO cost line there that just touches the ISO quant at point A. Okay? So nothing new from what we saw in the previous diagram. The firm wants to produce 10,000 units of output, and the way that it does that for the minimum cost is that combination there at A. A certain amount of labour and a certain amount of capital. And for the firm, that will incur a certain cost. And that certain cost is, using notation that we've seen before, that certain cost is C, whatever that cost might be. So, it implies a certain amount of labour and a certain amount of capital. It incurs a certain cost C. And so remember, this is the diagram we saw previously, the vertical intercept is total cost divided by the price of capital. Horizontal intercept is total cost divided by the price of labour. So that ISO cost line costs the firm C. And it implies a certain amount of labour and a certain amount of capital. Now what the firm does, it doubles everything. Rather than employing 1 unit of labour, it now employs 2. Rather than employing 1 unit of capital, it now employs 2 units for every unit of capital. So it absolutely doubles everything. Whatever it might have done before at point A, it doubles everything. What's going to happen to its costs? If you double everything, your costs will also double. If you employ a certain amount of labour, you now employ double the amount. A certain amount of capital, you employ double the amount. Your costs will double. Hence, that ISO cost line there is now not C over R, C over W, but it's 2C over R. 2C over W. Our costs have doubled. That ISO cost line is drawn twice as far out. We're anywhere along that ISO cost, costs are twice as much. So, by doubling its costs, by using twice as many factor inputs, the firm is able to produce more output. And the maximum amount of output it can produce would be where an ISO quant just touches that new ISO cost line. And that ISO quant is this one here, associated with 25,000 units of output. And so the optimal mix now goes to point B, using more labour and more capital. So we've doubled all factor inputs, and by extension, double costs, and it allows us to increase output. So the question I would ask you, what degrees of return to scale? If anyone hazard a guess? Is it increasing, decreasing or constant? Increasing, decreasing or constant? What have we done to all factor inputs? We doubled them. What's happened to output? Increasing, exactly, thank you. Thank you for volunteering as well. So, we've doubled all factor inputs. Our cost has gone from C up to 2. We doubled everything, so costs have doubled. In doing so, we're able to produce now more than twice the amount of output. Output has gone up from 10,000 to 25,000. It's more than double. So that was in our definition of increasing returns to scale. if output increases by a greater proportion than the increase in factor inputs. So we've doubled inputs, we've doubled all factor inputs, output has more than doubled. That's increasing returns to scale. So in this diagram here, we've got increasing returns to scale, but they still haven't quite got to the question we want to answer. We want to know something about the firm's long-run average cost. So what is long-run average cost? Average cost is merely total cost, which is RC, divided by output X. That's the average cost. Cost divided by output. Now I'm going to show you how that varies, how that changes, depending upon returns to scale. So the scenario that we've run through here is increasing returns to scale. Well, when we have increasing returns to scale, and I'll just give you the tagline for the moment, when we have increasing returns to scale, average cost will be declining. Now this is the part we've got to think through a little bit. But I've given you a very, very simple example just to show this. So, increasing returns to scale, average cost, long-run average cost will decline. Very, very simple example. Let's say that costs, our total production costs, are £100,000. And the firm is producing 10,000 units of output. If that were the case, long-run average cost is cost divided by output, C over X. 100 divided by 10 equals 10. So our average cost is 10. So that's our starting point. Long-run average cost is 10. Now what you need to do is think about what happens to long-run average costs if both cost and output change. And that's what we saw, I'll quickly put it there, that's what we saw in this diagram here. Costs increased, output increased. And we want to look at that relationship between the two. So in that example that we said, costs doubled. We doubled all factor inputs, and hence we doubled costs. It went from C to 2C. So that means a 100% increase in costs. So C has gone up by 100%. That caused output to go up from 10,000 to 25,000. So that's a 150% increase. So what have we found? We're finding that the change in C is of 100% is less than the change in output X, which was 150%. And so if we take these new values, costs doubled up to 200,000, output more than doubled up to 25,000. So if you put it in your calculator, work it out, 200,000 divided by 25,000 gives you average cost of 8. So when C increases by less than a factor, less proportion than output, X, average cost will be declining. It goes from 10 to 8. That is what we get when there are increasing returns to scale. The change in costs is less than the change in output. And as such then, average cost will be declining whenever there are increasing returns to scale. Always, always be the case. Increasing returns to scale, long-run average cost declines. Well, what about the reverse of this situation? If we found, for example, in this diagram, we started off at point A as before, then we doubled all of our factor inputs. We doubled all labour and all capital. We move again from that ISO cost line, that lower one, to this higher ISO cost line there. That allows us to again produce more output. This time though, the increase in output is from 10,000 units at point A to 17,000 units at point B. So we've doubled all factor inputs and doubled costs, but output has less than doubled. That happens when there are decreasing returns to scale. And very quickly, if you all finished copying that diagram down? Yep. Very quickly then, just to give you an example, just to illustrate that, start off the same as before, costs £100,000, output of 10,000, that gives us our average cost of 10. Now we doubled all production costs by doubling all factor inputs, so there we go, costs increased by 100%. But by how much did X increase by? It went from 10,000 to 17,000. It increased by 70%. So costs and inputs have gone up by 100%. Output has gone up by only 70%. So cost is increasing by more. Costs have gone up by 100%. Output is going up by 70%. Put those figures, 200 divided by 17 gives you around about 11.8. So average cost is increasing. It's gone from 10 to 11.8. And that will always be the case when the change, the percentage change in costs is greater than the percentage change in output. And that will occur when we have decreasing returns to scale. So decreasing returns to scale means that average cost will increase. Our long run average cost curve will be increasing. So you can see, long run average cost depends upon returns to scale. Increasing returns to scale, average cost is falling. Decreasing returns to scale, average cost is increasing. So now that that is clear, what can we say? Well, we can say a technology that exhibits initially increasing returns to scale before eventually decreasing returns to scale set in will have a long run average cost curve that looks like that. Exactly what we said at the beginning. I'll lead you all this way to a diagram that you've seen before, that you will know. That your long run average cost curve has that classic U shape. It will initially decline. Long run average cost curve will decline when we have increasing returns to scale. When firms are able to take advantage of production line techniques. When they're able to take advantage of specialisation of workers. That is that initial part there that drives long run average cost down. However, it then comes a point where firms become unwieldy because of their size, with diminishing or decreasing returns to scale set in. Increased bureaucracy, inefficiency, call it what you want, but it forces, and firms suffer for their size, and it forces long run average cost up. And it doesn't matter what our factor inputs are, it does not matter what precise production technology a firm is employing. Typically, the long run average cost curve is going to look like that. It will decline, reach a minimum, before eventually it begins to go up again. But we still haven't answered, I'm talking and talking and talking, but we still haven't answered our question. What is the most profitable level of output to produce? Well, if you look at the diagram, what have we got here? We have a price-taking firm. It does not matter how much output a firm produces, it will still charge exactly the same price level. Its actions, that's what we mean by price-taking behaviour. Its actions have no effect upon the market price it receives. Hence, where will profits be maximised? Profits will be maximised with a given price. They'll be maximised where cost is at its minimum. And there you go. That's what we've got in the diagram. That our long-run average cost curve. That shows us all the combinations of labour and capital a firm can produce at its minimum cost combination. And of all of those minimum cost combinations, the one that maximises profits is where the average long-run average cost curve for the price-taking firm is at its minimum. It will therefore produce X star units of output. And that is the profit maximising point for a firm in the long run. X star units of output combining ISO quants, and ISO cost curves to produce that long-run average cost curve. What I'm now going to do is, rather than giving you the full rendition for everything I've got in the slides, and for those of you who have printed off the slides, I do apologise, there's a few extra ones in there that you won't need. We've looked at the short-run labour demand schedule, that short-run factor demand, and we said that it sloped downwards. And we argued through that intuitively, using the idea of that profit maximisation between the wage and the marginal revenue product of labour. Well, I want to do a similar thing now in the long run. What does the firm's long-run factor demand schedule look like? So as an example, and this is merely as an example, we're going to take labour again. Let's say labour, we're going to vary that in the long run. And we say, and the precise example I'll use is an increase in the price of labour. We want to know, would a firm employ more or less labour? Now, if you've got the slides in front of you, and I will skip over these, I'm going to jump straight to the end and give you the intuitive answer. What does a firm's long-run factor demand schedule look like? If there was an increase in the price of labour, how would the firm respond? Now, do you think you've seen demand schedules in the past already? Demand schedules can do only one of two things. They can slope downwards from left to right, in the conventional case, or maybe with goods that exhibit different behaviour, they slope upwards from left to right. So those are the two possibilities that you've got. What does the long run labour demand schedule look like? Okay. The long run factor demand schedule will look like that. It will slope downwards. And there are lots of diagrams, complicated diagrams, that we could go through to prove that. But what I want to do is ask you to think about it intuitively. What I want you to do is think about it intuitively. Why does that long run factor demand schedule slope downwards? So the question is, we've looked at what would happen if the price of labour increased. Now, were that long-run factor demand schedule to slope upwards, what would that imply? That would imply that as the price of labour increased, the wage increased, a firm would respond by employing more workers. That's what it would mean if that slope upwards. What we're saying here is, if the wage rate goes up, if the price of labour goes up, the firm will respond by cutting the amount of labour it employs. Intuitively, why is that the case? Well, think about what would happen before the price of labour went up. The firm would look at the price of all of its factor inputs. It would look at the price of labour. It would look at the price of capital. It would see what output it could produce. It would see how much it could sell it for. And given that, the firm then identifies an optimal mix of labour and capital. Now, if it wants to, it could imply more labour. It could utilise more units of labour. But a firm chooses not to. And why does it not want to employ more labour? Because it's looked at its production costs, it's looked at its revenue, and said, look, the optimal thing I can do is employ this much labour. I've got the option of employing more, but it's not profitable to do so. It's cheaper not to employ extra workers. And so that's what it does. It chooses to employ a certain number. Now think about that profit maximising consideration. What would happen if the price of labour goes up? All of those units of labour a firm could have employed before, but chose not to because it wasn't profitable. Well, now that the price of labour has increased, it is even less profitable. So if a firm didn't employ them before the price went up, it absolutely won't employ those units of labour after the price has gone up. And hence, could that then be a logical response? Would you employ more units of labour? Would you employ more of a factor input when its price rises? No. Only thing you would do is employ less. And hence, our long-run factor demand schedule must slope downwards. There's no possibility of it sloping upwards in a conventional way, as we saw in the short run, the long run factor demand schedule. And even though I've talked about labour here, I've only used labour as an example. You could take the long run factor demand for capital if you want exactly the same arguments apply. The only response to a reduction, the only response to an increase in the price of the factor input is to reduce the amount you use. And hence, the long run factor demand schedule will always slope downwards.